Hi, in this video, I would like to provide a very short review on chapter 11, vectors and the geometry of space. Okay, so if we go from R2 to R3, right? Basically, we have vectors in here and vectors in here, and each vector in the plane can be considered like a point because each vector is corresponding to some to a pair of numbers, right? This is a point on the plane. This is a vector. At the same time, this can be considered like complex number because for this pair, I might have a equal to a plus ib. That is complex numbers, right? Uh, okay. How about a point or vector in the space? So for this, you have x and y and z, right? That is a point, that is a vector if you connect that point with the origin, okay? So basically, when you consider vectors in space or in the plane, the most important notion is distance function. Distance functions. We might have several kinds of different distance functions. So if you took linear algebra, probably you know about dot product and inner product, right, in spaces. Uh, in R3, we use dot product. We use dot product. And what is dot product? You have two vectors in here, so that is sum of xi, yi, right? I from 1 to 3, let's say that, because we consider three-dimensional space. So based on this dot product, you can define norm of vector. Norm of x is just x and then 1 over 2, right? You consider norm, and that's what you know, that is square root of x1 squared plus y1 squared plus z1 squared, right? I mean, in case x is x1, y1, z1. And then, using this norm, you can define the distance between two vectors. That is x minus y. That's the norm of this difference. So now you have distance between two vectors or distance between two points. And then you see, once we have distance, we have geometry of the space. So first, we have to remember about that, okay? We have distance, we have product. That is what we have. Dot product, by definition, dot product is sum of product of corresponding entries. And then using dot product, we define norm of a vector by this formula. And using the norm, we can define the distance between two vectors, okay? And now let's consider some, main geometric properties of the space. Let's say we have, when we talk about the space and vectors, the only one I want to share with you is the projection, because projection is very important. Let's say orthogonal projection, right? Or projection. Orthogonal. So what's that? Suppose you have one vector in here, that is u, and you have another vector that is v, and you want to find the orthogonal projection of u onto v. So this is projection of u onto v, right? The question is, why do we need such projection? We need such projection first, because if you want to find the shortest, the distance, right, from this point to this straight line, you have to find projection of this point onto this straight line. That means you have to find this point, right? and then the distance is equal to the norm of this vector, and this vector is say you have u minus projection of u onto v, right? So this problem is some kind of optimization problem to find orthogonal projection. Okay, that is important, and when you study linear algebra, I mean, if you did that, good. If you did not did that, that's fine. But here's an example. Uh, you want to find, this is a vector, right? Suppose you have two vectors and this guy are orthogonal, and you want to find components of u onto this and the component of u's onto this, right? So basically, projection of u onto v is the component, is orthogonal component of u onto this vector, onto this direction. So this is why orthogonal projections are important. Okay, let me remind you the formula. So orthogonal projection of u onto v is the product of u and v divided by v squared, the norm of v squared, right? The norm of v and x squared, and then you multiply by v. That's it, right? So let's say if you have u equal to 1 and 1 and v is 4, 0 and 4, you can find orthogonal projection of u onto v. U and v product, you take a dot product of this guy and this guy, you get 5, 1 is 4, 0, 1 with 4 is 4, so you have a, right? And the norm of v is squared norm. Square is 16, 16 is 32. You have 32 in here and then multiply by 4, 0 and 4. You simplify everything. 4 with a is 32, so you have 1, 0 and 1. This is how we find norm. Okay, so I think that is very first problem I want to tell you about the geometry of the space, orthogonal projection. Next, we may use orthogonal projections to define straight lines, right, or spaces, or planes. So yeah, here is straight line, right? If you fix some point A, x0, y0, and z0, and here you have some direction vector u, and here is b, which is x and y and z, then for any being here, vector AB is scalar multiple of vector u. So basically I can write A and B is equal to lambda u. And using this equation, you might have two kinds of equations of this straight line, which passing through a given point and then have direction vector u. So you might have x equal to x0 plus u1t, and then y equal to y0 plus u2t, and z equal to z0 plus u3t, right? Where u1, u2, u3 are coordinates of this vector. Or you might have canonical form of this straight line, which is x minus x1 over u1, y minus y0 over u2, and z minus z0 over u3. Yeah, some students might ask me, what happens if one of u1 or u2, u3 is equal to 0? So don't care about that. If that is 0, it's just 0, right? That means we don't write like x minus x0 divided by 0. This cannot be understood like division, okay? It's just very formal. All right, so now we have one problem with straight lines, right? Suppose you have some point outside of that straight line, Q, and you want to find the distance. You want to find the distance from Q to this straight line. That means you have to find this distance, right? Where this guy, P, is the orthogonal projection of Q on this straight line. Make sense? So you see, again, we need to work with orthogonal projection, right? So how to do that? In order to find orthogonal projection of Q onto this straight line, I will connect AQ, right? And basically this vector is the orthogonal projection. This vector is orthogonal projection of this vector onto this straight line. Okay, so once we get there, so you can calculate the distance by using Pythagorean theorem or something like that. So I will not remind you, I will not show you how to solve that. In the textbook, they have very good formula, which give you the connection between the cross product and then the distance from one point to the straight line. Here's the formula. D equal to norm of AQ cross product with the U divided by U. Divided by U. You know, actually, it's easy to prove this formula. It's nothing special in here. Because the cross product of AQ with the U, you know, AQ with the U is what? That is, you know, the area. That is the area of the base, you know, something like this. Area of this, right? This is the area. So you take 2 times, and then you divide by the U. Basically, U is this, right? You divide by the U, you get this distance. All right, so probably I will not solve any problem, just a very short review for you, or maybe we can do an example. Let's say I have this straight line, x equal to 3 plus t, y equal to 5 minus 2t, and z equal to 1 minus t. So vector u in this case, 1, -2, and -1, right? 1, -2, and -1. And a in this case 3, 5, and 1. So I have to, and I need to find the distance from the point -3, 5, and 1. Find the distance. Right? Find the distance from this point to this straight line. So this is A, and this is Q, right? I need to find AQ. I need to find vector AQ. AQ is equal to -6, 0, and 0. -6, 0, and 0. You take -3, subtract by 3, you get -6. And then you need to find the cross product of AQ and U. And then AQ cross product with U. That is the vector AJK, and then -6, 0, 0, and then 1, -2, and -1. You have to find this determinant, right? And since we have 2 zeros in here, I can expand this determinant along this row. I get -6, but -6 has a position 2, 1. So here I would have minus -6, and then multiply by JK1 -1, and that is 6 minus J plus K. So this vector is, I can rewrite in the form A0, -6, and 6. Right? So once you have this vector, you can find the norm of this vector, of the cross product, and you divide the norm of U, and you are done. I think the rest you can finish yourself. Right? Another application of orthogonal projection is we can use orthogonal projection to write equation of a plane passing through some point, right? And having a normal vector. So let's say how to do that. For example, if you have the point in here, right? You fix some point, and you fix some normal vector n, and you want to find you want to find the equation of the plane passing through A and orthogonal to n, right? So basically, if you take let's say this is x0, y0, and z0. If you just pick any point in this plane, suppose you have these x and y and z. So we always have AB this vector dot product with n is equal to 0. Because n is the normal vector of that space, right? So whatever you get in here, these two vectors are orthogonal. That means the dot product is 0. So from here you can see that is x minus x0, y minus y0, z minus z0, dot product with n1, n2, n3 equal to 0. And that is nothing but n1 x minus x0 plus n2 y minus y0 plus n3 z minus z0 equal to 0. And that is general equation of the plane passing through this point or fixed point and having n as a normal vector. And one problem with the plane is that if they give you 3 points, right, and they ask you to find the equation of the plane passing containing these 3 points. So how to do that? Suppose you have this one, you have this one, and you have this one, right? You have to find the equation of the plane of that 3 points, A and B and C. So the idea is as follows. You have to find n, right? You have to find n. And how to find n? We use very good property of the cross product. The cross product of two vectors is orthogonal to those vectors. So basically, in order to find n for this plane, I may choose AC and AB, right? And then find the cross product. That is AB cross with AC. Once I get the cross product, or I guess the normal vector, I have a point A, right? I can use this point, and then I write the equation of the plane. I'm done. Okay. The next question, in this chapter, is about different system of coordinates. Different system of coordinates. Usually we have x and y and z, right? And for each point x and y and z, or for each vector, we have 3 numbers, right? And these coordinates are called rectangular coordinate. Rectangular is because it's just rectangular, right? And but sometimes we need other system. For example, if you consider the plane x, o, and y, right? And how to define this point? Say, if I have x in here, if this is x, okay, let's say x0, y0, z0. If this is x0, and this is y0, then I can find this vector. This vector is x0 plus y0. This vector, actually. And then, once you have z0 in here, right? Z0 in here. You can add this vector with the z0, you get exactly this vector. Make sense? So this is the rectangular coordinate. But in this case, for example, if I want to involve some angle, right? Some angle here. This, I call this is theta. And then, okay, let me write x, o, and z, and y, right? This is this vector, you see? And this is theta, okay? So I want to involve theta, and so I can translate from this rectangular to cylindrical. Cylindrical coordinate, right? Let's say if this guy is r and this guy is theta. If we call the norm of this vector is r, so the relationship between x, y, z, x, y, r, phi should be x equal to r cosine of theta, and then y equal to r sine of theta, and then z is just the same, right? So the cylindrical coordinates is r, theta, and z. Okay, so how can we use this to go from one to another? For example, if you are given rectangular coordinates, right, and you want to find r, theta, basically you need to find r and theta because z is the same. So how to find r and theta? From here you can see tangent of theta is y over x, right? And then theta is arctangent of y over x. So you just plug y and x into that to get theta. And once you get theta, you can find r. Okay? But basically, from these two equations, you can see r squared equal to x squared plus y squared. So r is just square root of x squared plus y squared. So this is two system of coordinates, rectangular and then cylindrical. We still have another one, which is called spherical. So I want to involve the norm of our vector. We call that is rho, right? We call that is rho. And this is phi. So what is the relationship between rho, phi, r, theta, x, and y? Let's say, let me copy this triangle, right? In this form, I have the following one. And this is our vector. This is rho. And this guy is phi, right? This is 90. Okay, don't forget this is 90. And this is z. Okay, so from this picture we will see z is equal to rho cosine of phi, right? Z is equal to rho cosine of phi. And r, from this picture, this is r, right? Or this is r. Actually, this is r. R is here is r. R is rho of sine of phi. So thanks to this, I can convert cylindrical coordinates into spherical coordinates like this. X equal to rho sine of phi cosine of theta, y equal to rho sine of phi sine of theta, and then z equal to rho cosine of phi. And this is a relationship between rectangular coordinates and spherical coordinates. We have rho, theta, and phi. This is it, right? And then if you pay attention, what is rho? How to find rho, right? Suppose you have x and y and z. In order to find rho, when you take from these three equations, you will see rho squared is equal to x squared plus y squared plus z squared. And that is a very good property for the right parallelepiped, right? So I have in here x squared plus y squared plus z squared equal to rho squared. That's the first. And how to find theta? We already have theta, right, from here. What theta is from here? Theta is arctangent of y over x. Okay, so we have rho, the formula for rho, the formula for theta, and we need to find alpha. How to find alpha? Alpha, phi, how to find the angle phi? Phi can be found by using this formula. So you have cosine is equal to z over rho, right? From here you get cosine of phi equal to z over rho, and then phi is just a cosine of z over rho. Done. That's how we can go from rectangular coordinates to spherical coordinates. So I think that is all I want to mention in this chapter, and you have a couple of problems over there, right? Just using this three forms and all these formulas, you can go from one to another. If you want, we can solve one or two problems like that. But I think I will stop my reviewing here, right? Another problem in this chapter is we're concerned about different surfaces, and of course, since we have three different systems of coordinates, we might write equations, right, of our surfaces in different system of coordinates. Okay, let me consider one example and then we stop the review. So, for example, we have equation z equal to r squared sine squared theta plus 4r cosine of theta, right? And it's obvious that this equation is in cylindrical coordinates, right? Because we have z, r, and theta. We have r, theta, and z, right? That is cylindrical. And they ask us to find an equation in rectangular. So that means we have to translate this equation into rectangular coordinates. So we have to translate into rectangular. Okay, let's check that. The relationship between cylindrical and rectangular is x equal to r cosine of phi theta, y equal to r sine theta. And then z just z, right? So we do nothing with the z here, but we have to change this and this. Now you see, what is this? This is r sine of theta squared, right? And then plus 4r cosine theta. So by this formula, r sine theta squared is y squared plus 4x. That's why this equation can be translated into rectangular coordinates as z equal to y squared plus 4x. That's it, right? And how to understand, how to imagine about the surface or something, first, if you put x equal to 0, you get some parabola, right? Some parabola, but on the plane YOZ. And then once you add x, so you move that parabola around, you move that, right? And you make some change when x greater than 0 and when x less than 0. So basically, that is some kind of, if that x in here, y, and z in here, right? Z equal to y squared, where's that? Z equal to y squared, so that means you have something like this, some parabola like this, right? In the plane y, OZ. And then you add x, so that means you have some surface, but this surface some kind of this. When x less than 0, your surface just go into another side. When x bigger than 0, x goes to this side. Make sense? Okay, thank you for watching this video. I will make another video regarding vector value functions.